All right, let's look at number 17. They say here that 100 megajoules of energy is applied to an electron. When it's ejected, it has no kinetic energy. So what they're saying here is if it takes 100 megajoules of energy to, say, get this electron out of the atom, then you won't have any energy left. The thing will just be floating out here in space. If it took 100 megajoules of energy to get it out and you applied 200, well, then it would have some speed afterwards. But in this case, it would just be floating. So they want to know assuming you're applying 100 megajoules of energy, which electrons will require the most energy to eject from the carbon atom? Well, the electrons that are in the inside, these ones right here that are in the n=1 ring, are much closer to the nucleus. They're bound stronger. They're much further away from being ejected. So these would require the most energy to remove. And the ones on the outside, like in n=3, would require the least energy because they're closest to already being ejected. So if we go back and look at our question, which electrons require the most energy to be ejected? Well, you remember this number in the front is the n number. So this is ring 1, that's ring 2, that's ring 2. So the ones that are closest to the nucleus, which would be the 1s, would require the most electrons to remove. While we're here, if you did, and so 2s and 2p are not the answers, but because 1s is the answer. But if you were trying to decide between 2s and 2p, they're both, because they're 2s and 2p, they're both electrons in the second principal quantum number, the second ring. But that does not mean they require the same energy to remove. You'd have to come look at a filling diagram model. You see the nucleus is down here, there's the 2s, and there's the 2p. Which of these are harder to remove? Well, definitely the 2s, because they're closer to the nucleus, they're bound more strongly, and they will therefore take more energy to get out. The 2p's are closer to already being exited, so they would take less energy to get out. So just in case you had to work through that. Went the wrong way. All right, so then let's look at B. In B, we have the binding energy of a 2s electron is 80 megajoules. How many megajoules of kinetic energy will it have as it leaves the atom? And they are assuming you hit it with 100 megajoules of energy. So if we come in here and we say a 2s, like let's say this is the 2s electron they're talking about because it's in the second shell, and it takes 80 joules of energy to get it out of the atom, or 80 megajoules, and you apply 100, well, you will have definitely enough to get it out. And as a matter of fact, you will have about 20 megajoules left over. So that should be the answer. Don't worry about this electron volt here. We're going to assume an electron volt and a megajoule are the same thing. I don't think there's a unit conversion trick to this. All right, and then on to C. In C, how will the speed of a 2p electron compare to a 1s electron after it's ejected? Well, a 2p electron, let me write down what these are. They're in the second ring. So if we're talking about a 2p electron versus a 1s, since there's stuff on the other side, I'll put one here. A 1s, it's a 1s because it's in the first ring. Well, if you apply 100 megajoules of energy to each one, this one's going to take more energy to kick out. Like maybe it'll take 95 megajoules. And so you're only going to have 5 megajoules of speed kinetic energy once it's out. Whereas this one might only require, say, 70 megajoules to eject. That means you're going to have 30 megajoules of energy left over. So I think the 2p is going to be definitely moving faster. So if we look through our choices, it looks to me like the last one. 2p electrons will be moving faster than 1s electrons. Looks like the right answer.